Hello, moving on with this electrical fundamentals review video, we get to power. When we move charge from one location to another, we typically do work, we typically heat a circuit, or we light up a light bulb, which is kind of the same as heating a circuit, turn a motor, move a speaker, or something like that. So we actually accomplish some sort of work. We could accomplish a goal. And we measure the amount of work in joules. Technically, that's the amount of heat dissipated when 1 amp passes through a 1 ohm resistance for 1 second. That's the amount of work that is accomplished. Power is the amount of work done in a specific amount of time. It's the rate of work. So there's a time component to power that's really important to get. So it's the work divided by time, or joule, which is how much work is done. Joules divided by seconds is power. And we express power in watts. So summarize this all up, 1 watt is 1 joule of work done per second. So power is the rate of work. And we're going to use this term quite a lot, so let's throw it on the whiteboard. Power, the rate of work. I didn't really mention water yet, but if I did, it'd be the amount of work accomplished by the water flowing. If you were brushing your teeth, it'd be how many teeth you brushed in a certain amount of time with water, or how much hydration you achieved by drinking the water, that sort of thing. The letter is P, although we'll also use W because, of course, we're talking about wattage or watts. So there you go. Looks like the whiteboard is full now. That's great. Those are the terms we need to learn for this particular lecture. Let's look back at the water analogy, kind of clarify. We've got this beautiful water tower here. The height of the water tower, since this water really wants to flow downhill due to gravity, the height of this water tower, it creates a potential to do work, a potential for that water to fall and do something. Of course, move this water wheel, that we can measure that height in terms of voltage, which is pretty cool. And then the actual flow of charge through here, this is our current, the flow of water going down this pipe, coulombs per second. The coulomb would be a specific amount of water, like a gallon of water or something. So we've got our flow of charge here, which is our current. And then resistance, you can see this pipe is getting a little narrower. So the size of pipe, the length of pipe, the nozzle on the end of the pipe, those are all going to impact the resistance, which of course we measure in ohms. And now we got to the water wheel. The water wheel is going to do our work. I don't know what's attached to this water wheel, whether it's grinding some wheat or it's creating an electrical generator. Okay, that would be complicated. Let's ignore that for a second. But how much work is accomplished by this water wheel? That we would measure in watts. Joules of work per second accomplished. Cool. That works for me. So let's clarify a few things about the water analogy. Water, which is current, flows from one tank to another tank here if there's a difference in potential, which is voltage. So there's a difference in height here in this tank compared to that tank. So water current flows from here to here. So pressure doesn't flow, right? What voltage doesn't, the voltage is the pressure here. Voltage does not move from here to here. Current moves from here to here. So water flows, or current flows, because not water pressure, not voltage. So that's important. A lot of students get that confused, that current's moving, not voltage flowing. Not voltage is moving. So in bold down here, current flows through a circuit because voltage is applied across the circuit. That's really important to understand, that that voltage actually causes the current. So current is the flow, but you need the pressure to push it, okay? So there's our buddy Ohm, George Simon Ohm, and he was a German physicist, and he was the one who quantified the relationship between these three electrical phenomena. And this equation, which of course you've used before, is Ohm's Law, and it's very simple, and it shows us that current is directly proportional to voltage. So voltage goes up, current goes up. But current is inversely proportional to resistance. So when resistance goes up, current drops. So the greater the resistance, the less the current. The less the current resistance, the more the current. And of course, the greater the voltage, the more the current. The less the voltage, the less the current. And that phenomenon is really important to understand. And of course, we'll do some simple calculations. Here is Ohm's Law again, shown in a couple different formats. One is really brilliant how it all works, how 1 volt is equal to 1 ohm equals 1 amp to 1 watt. 1 volt, here's our 1 volt battery, across a 1 ohm resistance will generate 1 amp of current. And it will consume 1 watt of energy, of course, in 1 second. So this is kind of neat. This will show you how Ohm's Law works and how they all interact together. You, of course, if you haven't done so already, need to memorize 2 pie charts. The first one is this one, the V equals IR, or oftentimes you will see this as E, because E and V become rather interchangeable. So V equals IR, so this is saying, hey, volts, and when you're doing your simple calculations, I always put my hand over or cover up the letter that I'm solving for. So if I'm solving for volts, my equation would be I times R, which of course is amps times resistance, or current times resistance will give me my volts. Or if I'm solving for amperage, or I, or current, I would cover up I, and then I would see the equation that it's volts divided by resistance. Or if I'm solving for resistance, if I'm solving for ohms, I would cover up the R, and that would mean that volts divided by current would give me the answer. So you need to memorize this equation if you haven't already. Its sister equation, also known as Joule's Law, incorporates power into it. And so it's a similar idea. You cover up what you want to solve for. If you want to solve for power in watts, you cover P, and it's going to be I times V, and et cetera, et cetera. I won't explain all the permeations of this, but you cover up the one you're looking for. So you definitely need to memorize these 2 equations to solve these 2 pie charts, and you probably already have. So enjoy your homework where you get to refresh these basic calculations. I hope this little mini lecture or these 2 little videos helped out in getting your homework done. Have a great day. Bye-bye.